Yes. Anytime is on for this. Right? 26, 25th,
I'm probably sending more announcements than some fully online classes. Does anyone still take any fully online classes? Yep. Okay. How often do you get some announcements from the professor? I guess once a week. Okay.
Like usually it's like once a week, like he tells us what we're doing in the week and then he'll like make an announcement, like take your quiz today, take your test today.
Oh, okay.
So that's
Okay, that's good. At least you get some reminder of, where the class is supposed to be at. Great. We are. So we got 1 minute and 20 minutes.
25. Oh, I understand. 25, that's tomorrow. It's not that. Maybe the designers. But actually seems big. Where did you get it now? Oh, well, then I guess that was the right one. Which cousin did you go for? Well, yeah, but in there, there's like 3 options.
Gives you priorities. Rank it anyone singles or singles.
I'm pretty sure there's also another option.
Oh, studio? Yeah, studios I really spent.
What is the price?
Studios.
All right, so we got, okay, it is noon time and I guess we have some people participating online. All right, you guys ready? Okay. All right, so we're gonna get the class started right on time. So I got a few announcements to kind of remind people about things that are happening. We have 2 questions, they were actual questions, in the final exam in the previous semester. So, that's both a practice of, how you can apply the things that we have learned in counting and discrete probability, but it is also, related to the final exam for this class as well. I'm not sure how many of you have tried to copy and paste the question into Chat GPT, because, at least with one, I think at least with the growers question, Chat GPT was able to answer that, with a perfect answer. And that was 3.5. It missed one little thing, the fraction was the other way around, but otherwise he got a perfect score. I'm pretty sure Chat 4.0 is going to get the job done correctly. The other one I have not tried, friends in the queue. So we'll talk about the solution of those 2. The final exam time date is already in this announcement. I believe it is the 15th of May from 12:45 to 2:45. Since it's also in the class calendar, that means if you have set up your personal calendar on your mobile device to sync with the Canvas calendar, it would also appear automatically on your calendar, which I find to be quite useful. So that's an option that you can consider doing if you want to make sure that your personal calendar stays in sync with the school stuff. So I highly recommend it, but it's up to you to decide whether you want to have all of those events popping up, coming from your classes. Do we have any questions before we get started with one of these two questions? No questions? All right. And we got three people online. Can you guys hear me online? Yeah. I'm just gonna check with the chat. That is online. And okay, so we got a question. Oh, somebody got a question. So Ivan, if you have a question, go ahead and ask the question in voice, please, because it's harder for me to keep an eye on the chat channel.
You already answered my question, so we're good.
Okay, all right. Thank you. All righty. And we just got one more person online. All right, so we'll go ahead and start with the grower's question. And the exact text from the exam is in the announcement itself. So I'm just going to click on the announcement. It's exactly the same thing, in the original document. All right, so are there any questions about what it is asking? About understanding the question itself? Nope. Okay, I'm not hearing any questions. All right, so what we'll do is the first thing we need to do is to map this question to things that we have learned. Okay, that's the first step to answer any question in an exam, is to understand the question enough so that you can refer back and say, this question is reminding me of this type of thing. So the first thing is, if you look at the question, what it's asking you is computing the probability that the grower will indeed have at least 60 seedlings. So this means it has to do with chances, and we only talk about discrete probabilities in this class. So that means there's only one type, or there are only a few types of distributions that you have to worry about. So then the next question is, with all the probability stuff that we have talked about, they're all based on experiments. Okay, so now you have to ask yourself, what is the experiment and what is a trial of this experiment? Because once you characterize, each trial and then overall the entire experiment, then that itself would point you to the right, definitions and to help you calculate the solution. So tell me, what is a trial? Okay, in this case, what is a trial? We'll start with a trial, which I actually talked about a little bit last Wednesday. So what is a trial? What are the possible outcomes of a single trial?
Pretty sure a trial is a seedling and it either germinates or it doesn't.
Exactly. Okay, so each trial is trying to germinate a single seed and see whether it is successful or not. Okay, very good. So that means it has two possible outcomes, either successful, yes, we ended up with a seedling, or no, the seed did not germinate. All right, so the next question is to ask, if that is the case, if the first seed succeeds in germinating, does that prevent the second seed from germinating? In other words, are we dealing with a case where the result of the first trial removes possibility from the second trial? Is that the case? It is not the case. Okay, very good. So that means every single trial has two possible outcomes. Okay, and then how many trials do we have according to this question? So I'll give you three possible answers. Do we have 10 trials, 60 trials, or 70 trials? 70 trials, that's exactly right. Okay, we got 60 spots to grow whatever crop, and then we want to pad a little bit, so we have 70 seeds to germinate. But we only need 60 or more, right? So 60 is the minimum that we need. Okay, very good. So now we have characterized the experiment. The experiment involves 70 trials. Each trial has two possible outcomes. So with that in mind, we have narrowed it down to one single possible distribution. And what would that be? The success rate is 82% or 0.82. So that means, it's not even, right? So what distribution would that map to? I'm going to do the gesture here. People cannot see online. We're flipping a coin, exactly. So this is, going back to flipping a coin. This is almost exactly the same as flipping a coin 70 times. And we want to look at the chances of at least 60s of the coin flipping lands on the head, which has a probability of 82%. All right. So what is the name of that distribution? That's one of the last topic that we talked about on last Wednesday. Since it has to do with 2, it is by binomial. Exactly. This is the binomial distribution. And so now we can start to look into the equation of how to get this done. All right, so I am going to use Zernal. So this way I can actually write it out. All right. All right, so can someone tell me the overall binomial distribution thing? And also, where do we find the definition? Because the definition is definitely somewhere in the written module. So in the final exam, you kind of have to remember, the definitions. Where do you find all the equations? Where do you find all the formulas and so on? So you guys remember how and where to find the equation. Okay, I'm gonna take the silence as maybe, maybe not. All right, so this is where we go to find the definitions. So in Canvas, you go all the way down to discrete probabilities. There we go. And then we go to counting. Actually, we go to discrete probability. I cannot remember. I think it's counting or discrete probability. I think it's discrete. Yeah. And then we just have to. Okay, the first thing you do is you look at the table of contents, and then we look up the binomial theorem or binomial distribution, and it is this thing here. All right, so this is the binomial theorem, and you look at this thing and go like, okay, how is that going to help me? Because P is 0.82 in this case, and then Q is 1 minus 0.82, which means P plus Q is going to be 1. 1 to the power of whatever is always 1. Well, this by itself is not going to be helpful, okay? But this is going to be helpful. So if I scroll all the way down here, this is going to be helpful. All right, so what is it saying? If you want to find the probability of having M outcomes out of N trials, and the chances of the outcome that you want is P, and then the chances of the outcome that you don't want is Q, then this will give you the probability of exactly that. So the question is, what is N in our case? In this question, what is N? N is 70, which is the number of trials of the entire experiment. Okay, very good. So N is 70, and so this is 70, and this is also 70. Now the next question is, what about M? Because all I want is to have at least 60 seedlings, which means if I have 60, it's good, barely. If I have 61, it's good. If I have 62, it's good. If I have all the way up to 70, it's also good, right? So we are not looking at one single M in this case. The M is going to range from where to where?
60 to 70.
60 to 70, very good. So when you look at the equation that we need to work out, it's going to look like this. So it's going to be a sigma notation where I starts from 60 because we need at least 60 seedlings, but we can end up with 70 seedlings. If every single seed germinates, then we have 7 seedlings. And then the equation has N, which is 70, choose I, which is the number of seeds that will actually germinate, times 0.82, which is the chances of actually germinating to the power of I, and then 0.18, which is the chances of not germinating to the power of 70 minus I. And that becomes the answer. So do we have any questions about the first question, the one about growing and germinating seeds and stuff like that? Okay, So in that particular question, I think the question specifically said that you do not need to tell me the number. Instead, you can just give me the, okay, where did I get? Okay, now to go back to the announcement, go back to the question, but I believe it only asks for the sigma notation. So for this answer, you're explicitly required to use the sigma notation to express the probability. No actual numerical value is expected, which means if you do end up, because you have a super duper graphing calculator that can do all this with a single click, okay, give me the number, but it's not needed. Otherwise, the instruction of the exam is applicable, which means you have to provide the explanation. Are we good with this question so far? Are there any questions about how I arrived at the solution? Yes.
0.18.
That's 1 minus 0.82. Because P and Q are complements of each other. So if 0.82, okay, let me go back to this one here. So if 0.82 is the chances of a seed germinating, then 0.18 is the chances of the seed not germinating. So that's the relationship between the P and the Q. So P is our 0.82 in this case, and then Q, which is 1 minus P, is our 0.18 in this specific case. Yep.
What if the question has to say that we need 60 to germinate in probability 0.82? So how many seeds you need to get 60 of them?
Well, that's a very interesting question. Okay, so let me repeat that question so that people online can also hear that question. So the question, so what you mentioned was, what if the question is asking how many seeds do we need to germinate to make sure that we end up with 60 seedlings to put into all the pots, right? Mm-hmm. Okay, so in that case, there's no definite answer because unless your germination rate is 1.0, there's no way to really answer that question. Because as long as there's a very slight off chance that the seed may not germinate, then it is possible that no matter how many seeds you try to germinate, that you still don't end up with at least 60 seedlings. So it would be impossible to answer the question. Now you can change the question a little bit and say, with what if I just want 99.999% of certainty that I will end up with at least 60 seedlings? Then there's a way to answer that question. Because now you can just basically test it out and say, okay, if I was to germinate 100 seeds, for instance, okay, and I just really need 60 in the end, then you plug it into here, change the 70 to 100, and to see whether that is meeting the requirement that you want or not. So you can at least iteratively change the 70 to 71 to 72 to 73. So you can at least iteratively try to figure out what number will in the end give you the certainty that you want to have at least 60 seedlings ready for the spring.
So in that case, this might not do 61. Huh? So in that case, this 70 seeds might not do 60.
This number, this is a probability. I don't know what exactly number it is. I'm just going to guess. Okay, let's just say it's 75%. So this means, if I were to germinate 70 seeds or try to germinate 70 seeds, there's a 75% chance that I would end up with 60 seedlings. So there's always an off chance that you may not. The only other definite answer is the germination rate is exactly 0. Then no matter how many seeds you try to germinate, you won't have 60 seedlings.
Planting rocks.
Yes, that would work. Planting rocks. Yep, or fossils. Rocks that was once a seed or seeds. All right. So any other questions about this one? This is the binomial distribution. Are we good so far? All right. So we're going to move on to the next question, which has to do with friends waiting in a line in the school. I mean, probably elementary school. So in this case, we have a few friends. I think there were 5 of them. So we have Tristana, Ishan, Jane, Lashes, and Aplin. So 1, 2, 3, 4, 5. So indeed, we have 5 friends. And they are arriving at school, kind of in a random order, along with all of their peers. of a total of 26 students. So we have 5 people who want to be standing together as they are waiting to get into a classroom out of 26 people. And we also make the assumption that the arrival order is completely randomized, that there are no known distribution to that, okay? So the question is asking, what are the chances that these 5 people will end up actually standing next to each other, on a particular day, assuming there are no absences from the rest of the class? Okay, so how do we solve this problem? I gave you like in this really simplified example, right? So the really simplified example is simplifying to only have 4 students, A, B, C, and D. And then we have A and B being friends, they want to be together. And then we have the rest of the class, that are also coming in, different times, and it's completely randomized. So did you guys try to use that clue to try to find the answer? Okay. Yes, most people, some people did, okay, but I'm guessing not everybody did. All right, so I'll go through a quick explanation of that part. Okay, so we have A, B, C, D. There are 4 students. And so the first thing we need to look is, how many ways can these 4 people arrive in different orders, okay? So before I even write it out, how many possible, okay, are we dealing with permutation or are we dealing with combination here? We are definitely dealing with something that has to do with choosing, right? So if you imagine all the classmates or all the students in the class in a bag, I'm just picking one at a time. So are we putting these into another bag where the order is not important, or are we putting these into a tube where the ordering is important? Ordering is important. Very good. Okay, so if ordering is important, are we counting permutations or are we counting combinations? Permutations, very good. Okay, so we are looking at a permutation of 4 choose 4 because we're using all 4 students. No one is missing, no one is absent in this case. So if you look at P4 of 4, or the number of permutations of 4 choose 4, it is 4 factorial divided by 4 minus 4, the whole thing factorial, which is basically just 4 factorial divided by 0 factorial, which is 4 factorial. And tell me what is exactly 4 factorial. It's 4 times 3 times 2 times 1, which is 24. Very good. Okay. So now we have 24 ways of these 4 students to arrive in different ordering. So now the question is, how do we figure out the number of permutations are the ones that we want? In other words, we want A and B to be together, but the other 2 students, the C and D, they can be anywhere. So how do you approach this problem? So 24 is also the cardinality of omega, because remember, omega is the set of all the experiment outcomes. So that part is done. What we want to know is the cardinality of E, or the set of events, or the event set. Okay, so how do we process this problem? Okay, so if you have put some thoughts into this over the weekend, what I'm going to tell you is going to click right away. So you basically look at A and B as one person. Okay, you look at A and B as one person. So now we only have 3 people in the class. And then you ask, how many ways can we arrange these 3 people? In other words, you're basically handcuffing A and B together. So they have to arrive at the same time. Is that okay? So that's an easier problem. Okay, so we'll just say, A and B, we'll make a new student called E. Okay, E is representing, E is A, B together. Oops. Okay, there we go. So now we only have C, D, E, right, as possible students. That's an easier problem because we have C, D, E as one permutation, C, E, D as one permutation, E, C, D as a permutation, and then we have D, C, E as one. The other one is D, E, C, and then we have E, D, C. There are 6 permutations. Does that make sense to you? Because we have, once again, the number of things that we can choose from is 3. The number of things that we want to choose is also 3, but we are also counting permutations. So we are looking at P of 3 comma 3 in this case, which is just 3 factorial, which is 6. Is that okay? But that's not the end of the story, because otherwise you would say, 6 out of 24, but it's not 6 out of 24, because we are forgetting that even though A and B are handcuffed, they can still switch order like this. In other words, E has 2 possibilities, because E can split out to AB, E can also split out to BA. So the actual number of ways is not just the 6, but you also have to multiply by 2, because AB and BA can switch order within the container of E. So we have 6 times 2, which is 12 in this case. So this is actually the cardinality of our event set. So that means the probability is going to be the cardinality of the event set, which is 12, divided by the cardinality of the experiment outcome set, which is 24, which is 50-50 in this case. It's a 50% chance that A and B will arrive so that they can stand next to each other. Are we doing okay so far? All right. So this is where, I'm trying to teach you something that would extend out of this class, is to look at a smaller example where you can just kind of enumerate everything so that you can get a feel of what you're dealing with, and then try to extend the solution of the simpler problem to the problem that you're given with, which is a lot, it's a little bit more, because if you are to draw out 26 factorial, that's not something you want to do on a piece of paper or a pile of paper for that matter. You can write a program to do it, but I wouldn't do it by hand. So what are we dealing with here? So we are dealing with, this 4 factorial is coming from the total number of students. Okay, so instead of 4, what do we have in the question? Let me go back to the question itself. We have 26, that is correct. So this 4 here is a 26. So we have 26 factorial being the cardinality of big omega. Do we have any questions about extending? Oh, you guys cannot see it because I forgot to switch to the screen here. So are there any questions about 26 factorial being our new cardinality of big omega? Okay, because you have 26 students, they arrive at random order, and there are 26 factorial ways for these 26 people to arrive in a line. Okay, that's good. All right, so now we take a look at this 6 factorial here, okay, or 3 factorial, sorry. Good. Go ahead. You go first. I just couldn't hear you the first time. We're combining the people who want to be together as one single group.
Yeah, that's what I was gonna say. We're looking at our success case.
Yes. So in our case, we want 5 people to be together. So how many unique groups do we have to consider? Instead of the 3, what would that be in our case?
21.
It would be 26 people minus 5 plus 1.
So 22.
So we got 22. Yep. So the 3 factorial becomes 22 factorial. Okay. So 22 factorial is the number of ways to arrange people in this group of 5 people. So instead of just handcuffing 2, which is A and B in our example, you're now handcuffing 5 people. Okay, I'm pretty sure that's illegal in any type of school district, but for the sake of this example, just so that you can remember this more easily, we'll just imagine that you are handcuffing 5 people, so they have to arrive together, right? Okay, so what about this factorial, this 2 factorial here? What is that accounting for? Why do we have to multiply by 2? It has to do with within the group, okay? The people who are kind of cuffed together or glued together or however you want to kind of stick them together. There's the internal ordering within those 2 people in the example. So in our question, what would that 2 factorial become? How many people do we have that we want to arrive together? We got 5, right? Exactly. So now we turn this 2 factorial into 5 factorial. Okay, so let me use a different color. So this way we can see what we have. So we got this 26 factorial here. We got this 22 factorial here, and then we got this 5 factorial here. How do we combine these 3 individual things to come up with the cardinality of E? Well, first of all, this 6 factorial, okay, this 6, which is a 3 factorial, becomes the 22 factorial. Okay, so the answer is we have 22 factorial times the 5 factorial, okay, as the number of ways for the class to arrive where those 5 people are together. Does that make sense? So let me just say it one more time. The 22 is coming from treating those 5 students, the 5 friends, as one single unit, combined with the other 21 people in the class. So you have 22 unique units. And this explains how many ways that can be arranged if those were to arrive in random order. But within the 5 people who arrive together, we also have 5 factorial ways of arranging those 5 people within themselves. So this gives us the cardinality of the event set. So this becomes that. The cardinality of big omega is 26 factorial, because in this case, we just want to say, okay, if we don't want any particular thing, okay, and people are just coming in at random order, how many ways can they come in? Okay, how many ways can that be arranged? And that will be 26 factorial. So the answer is 22 factorial times 5 factorial divided by 26 factorial. That would be the probability of these 5 people arriving in its own group so they can stand next to each other. And that's a pretty small chance. All right, so do we have any questions about how this one is answered? Yep.
Is there a plus 1 at the end? The 26 minus 5. So
Because 26 minus 5 means you have the other 21 students who are not part of the friend stuff. But the plus 1 means we are adding the entire group of the 5 friends as one single unit. So you have to remember to add that 1 back into the number of choices in the bag.
okay, so you're consolidating to the 5.
Yes. That's why you have to plus that 1, because we are combining the 5 into one single group. Yep. So are we good, doing okay so far? If you guys want to, you can kind of copy and paste this question into ChatGPT and see whether it can give you a satisfactory answer, even better than mine. I would imagine that I won't be needed anymore in the near future. It would be kind of funny if you can ask ChatGPT, like, I have an exam coming up, ask me a tricky question related to blah blah blah, so you can practice. I've never tried that, but it's a possibility, right? I mean, especially if you're talking about calculus or something that's well established.
You probably also take your exam questions, feed in past exam questions, and then say, write me a similar exam question for these.
That is a very interesting idea. We can have a tech GPT.
And it'll give us written out solutions.
Yes. Yes, go ahead.
Literally, instead of like, so people have been using it, like they feed in their essays, but they also feed in their rubric. So like the AI would create it.
Right. It's not necessarily a bad thing. I mean, if people do it so they can get a higher score, as if they turn that in as their own, it is not a good thing. But if they do that just to learn about, so they can learn about how to improve themselves, that's actually a really powerful way to learn. Yep. Yep. Go ahead.
So if we change the question a little bit, what would change? Is we have 30 students,
Mhm.
A, B, C wants to be together, then IJK one, two together.
Ooh, so you got two groups, right?
Yeah,
It will be very similar, except, you will end up with, so ABC, you have those three combining into one group, and then you will have DEF combining into one group. So it's gonna change this portion,
that's what I
So-
want to understand.
it will change that portion, but it will also change this portion here, because instead of using just one single factorial for the group, for one single group, now you have two groups. So you will have a 3 factorial for the group of ABC, another three factorial for the group of DEF in that case. But the same approach will work.
And then 30 minus 6 or 3.
It will be 30, okay, so if you really want to boil down to, how we are combining and then adding the group back, it'll be 30. Okay, so I'm gonna use the next page here. Give me a second. Okay. So you have 30, but then you minus 3 plus 1, minus 3 plus 1, because you have two groups, right? So this will give you, in the end, it's going to be the same because you have 24 plus 2, which is 26. So you have 26 factorial as the denominator. The numerator is going to be, oh, I take it back, sorry.
30.
Yeah. It's 30 factorial as the denominator because that's the cardinality of omega. And then on top, you will have 26 factorial times 3 factorial times 3 factorial. Because you have ABC having 1 factorial, so that the students within that group, you account for all of those permutations, and then the other 3 factorial to account for the other group, which is DEF. So it would extend to that question as well. Yeah, very good. I like these questions because you guys are thinking, oh, okay, so if we can solve this problem, can I extend the approach to solve a similar but slightly more complex question? So that's a really good line of thinking. All right, so are there any other questions about the 2 practice questions that I posted from last Wednesday? Nope. Was it helpful or was it not helpful at all? Did it get you guys to start to think about these things? I mean, I'm not expecting you guys to come up with a solution like quickly, but it started you thinking. Okay, very good. All right, so what we'll do next, according to Joplin, is we are now back to the big O notation. All right, so I hope you guys found some time to kind of read about the big O notation over the weekend. And I just have to go find that thing here. It's right there. All right, so we talked about, okay, so just a recap of what we talked about before. Supremum is basically the maximum, because if we are talking about numbers, whether it's real number or integer, doesn't matter because they are totally ordered. If they're totally ordered, then the supremum is the same thing as the maximum. We also talked about infimum, which is basically the same thing as the minimum. Okay. We also talked about the limit of a sequence, which basically means, no matter how small of a number you give me as an epsilon, I will just have to go further down in the sequence and say that everything after this, point in the sequence is going to be this far away, epsilon away from the limit, which I call k in this case. So we are talking about this notation here. Is that okay? And then we also talked about how this is, well, it's not going to work even for a sequence that is as simple as xi or x subscript I is just negative 1 to the power of I. Because what it does is just alternates between 1 and -1, 1 and -1, 1 and -1. So if you guys are to ask, okay, Tag, here's your epsilon, it is 0.5, okay? I cannot give you the limit. There's no way I can find you a limit because the amplitude of the oscillation is fixed. It does not taper off to approach to a particular single line. Does that make sense? Okay. So what we'll do next is to say, well, but what if the time complexity looks like this? Okay, it ends up with some kind of oscillation where the amplitude does not attenuate or does not become smaller over time. So now we talk about limit superior. And this is a combination of the concepts that we have talked about so far. And of course, we have all of these funky symbols that you guys will have to now start to interpret. All right. So can someone tell me what limit superior really means? In other words, this is the notation of limit superior. This is how it's defined. So can someone describe, what is it exactly? Okay, first of all, it is a value of some kind, okay? The next question is, what kind of a value is it? So if you are to replace infimum with minimum and to replace supremum with maximum, it might be a little bit easier to read. So we are looking for the minimum of the maximum, and depending on where we start in the sequence. Is that okay? Okay, probably not. So I expanded the whole thing a little bit here. In other words, let's just take one of those quantifiers out, and we just basically say we basically look at this n is greater than or equal to 0, and we just expand it and say, oh, okay, well, if n is a natural number, it can be 0, it can be 1, it can be 2, and so on. So with this one here, just focusing on this portion here, do we understand what we are looking at? Ignoring the infimum, okay? Just focus on this part here. Now, this is what I'm talking about. It's difficult to express using Zoom because I'm using two hands, right? I'm doing like this range here. So in Zoom, it's hard to imitate that because I only got one single mouse pointer. So I can only say within this range here. But do we know what that means? We are looking for the supremum or maximum for all the k, x of k's, as long as k is greater than or equal to 0. What does that mean? Yep.
When you say supremum, is it just the maximum or the?
It is just the maximum.
It's not the lowest.
It is, it's the, okay, so by definition, supremum is the smallest of the upper bounds. It's the lower of the upper bounds, right? So it is the maximum, which we know as just the maximum. Yep. So that is just the maximum of all the k of the x of k's, starting from the very beginning of the entire sequence. Does that make sense? Okay, so this entire first item here is really just saying, okay, what is the maximum of the entire sequence? Is that okay? All right. What about the second one? Okay, look at the second term here. Okay, what I'm using my mouse pointer here to point out. How is that one different from the first one? Yes.
The maximum of all this, the entire sequence except for the first.
Exactly. So we are ignoring the first of the entire sequence and we're asking, what is the maximum of the second item all the way to infinity? Okay. What about the third one? Ignoring the first two, what is the maximum? And then we just go, ignoring the first three, what is the maximum? Ignoring the first four, what is the maximum? Ignoring the first five, what is the maximum? And so on. Is that okay? So we have all of these maximums with a different starting point in the sequence. And then what do we do with all of these things? What is that? What is INF? Infimum. So infimum is the fancy word of minimum, right? So we are finding the minimum of a bunch of maximums. And the maximums are based on the starting point of the sequence. Okay, we start with the first one, which is asking, what is the minimum, what is the maximum of the entire sequence? What is the maximum of everything but the first one? What is the maximum but the first two? What is the maximum but the first three? What is the maximum but the first four? Blah, 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 and so on. That defines limit superior. Is that okay so far? No. Okay, I think this will help. So we're going to use a graphical approach, okay? So I'm just going to show you a graph here, where it is some kind of an oscillation, okay, like so, okay? So assuming the oscillation stays at this particular amplitude at the end, so the end amplitude here is going to stay. What is the limit superior starting from this point? What is the maximum starting from the very first element of the entire sequence? It's going to be here, right? Because this point is after this point here. So it's going to be like this, okay? So the limit superior, or I should say, yeah, the limit superior is going to be the same for the first elements all the way up to this point. And then, okay, let me choose a different color. I think this is going to work. So if the blue line is indicating the limit superior, and of course, in this case, this axis here is just going to be K. It is telling us which element in the sequence we are looking at. Is that okay? So from here, we kind of have a drop. And I have to be careful where it drops to. So it's dropped to this point. Because if you start like from here, and you ask, what is the maximum starting from this point all the way to until the end of time? Then it's going to be, well, it is still the maximum at that point. But then when you look at these two peaks here, there's one peak here and one peak over here. This is the highest peak. So this particular peak means that the supremum, okay, I can't really draw this without a ruler. So we're gonna pick a ruler. I know there's a ruler somewhere. Nope, it's not this tool. Tool. There we go. Do we have a line? Yep. Okay, there we go. So now we can draw a line from, that's the wrong place there. Maybe from here. Yep. All the way to here. Close, but not exactly. Just imagine they are touching. Okay, so the blue line is indicating the maximum with a different starting point. Okay, so from this point here, okay, this is why I think it's good to teach entirely face-to-face, because I keep forgetting that I have to go back and do it now. So starting from here, the maximum is all the way over here. So the maximum is going to stay all the way here. But then once we get here, the maximum is going to go down to maybe about this point here, right here. And then we draw a straight line to here. And then I turn off the ruler tool. And then from here, it's going to drop down a little bit. And then it'll be a straight line again. And where's my line? There we go. From here to here. And then from that point, we are going to drop again to here, and then a straight line over here, and then drop here, and so on. Are we doing okay so far with what the blue line is trying to figure out? It's just that, at a certain starting point, say this is my starting point here. I'm asking from this point all the way to the end of the line, what is the maximum? Well, let's figure it out. Well, this is pretty low, and then it gets higher, and get lower, and get higher, and get lower. This is the highest point, all the way to the end of the entire curve. So this maximum becomes the maximum of this point if I were to start here. Is that okay? Is that concept okay? Okay, yep.
Would you like program this? Because if you're trying to find the next nice peak, wouldn't you have to go through the entire?
That is correct. If you are to do this, using a programmatic way, it would not be doable because the sequence is infinitely long. Right. Yep.
I was just gonna say, if you did have a finite data set, then you would probably want to work from the backwards, right? Because then you could just keep track of the max.
Yep. And this reminds me of there's a problem in lead code of finding the best time to invest money. So if you want to kind of sharpen or test your programming skills, look up lead code, and there's a problem. where it starts off with, just, doing a local optimization, like when to buy and when to sell, and then went to a global optimization of what if okay, the forecast of how the stock is going to rise and drop, which has some similarity of what we're doing here. But it's an interesting programming exercise. So if you got spare time, and you want to test out your programming skills, I totally recommend that particular problem. Okay, so but getting back to our discussion here. So starting, let me make sure that I don't have the ruler turned on. But starting from here, we can basically just say that, well, it's just going to be a straight line all the way through, because you remember what I said, the oscillation amplitude is not going to change after that point. Is that okay? So this is limit superior. So what about the entire thing? What is the limit superior of this entire sequence? So if I were to use the green line here to indicate the limit superior, it would be, okay, this is going back to this, drawing a straight line. This is our limit superior. In other words, even though we can have some fluctuations and the value can go up, it never drops below this line until, all the way until the end of the entire sequence. Yep.
It's just a value that we can plot on a graph, like y equals 3 or something. Is that what it is?
Well, this is totally a made up curve, but the time complexity function itself may exhibit some of this kind of behavior where it does not have a limit itself, but it has a upper bound to the limit as you continue to infinity. Is that okay? All right. Cool. So the green line is representing limit superior. The blue line is indicating the maximum at a particular starting point. Is that okay? So I want to make sure that you guys understand what the colors are meaning in this case. All right. So if there's limit superior, what do you think has to be a complement to limit superior? Limit inferior, exactly. So limit inferior in this case is drawn exactly the same way, except it's upside down. Okay, so if I were to use, let's choose a different color here. Let's try orange. So if the orange line is the limit inferior, it's basically giving you probably around this line here, which is, so between the green line and the orange line, that forms an envelope to basically say, past a certain point, the upper limit, the upper bound and the lower bound would be between these two lines. Is that okay? So the main difference between a limit and using limit superior versus limit inferior is limit is a combination of the two. So the limit that we have talked about before is basically saying limit superior and limit inferior are exactly the same thing. When you draw the line out, then they merge into one single thing. This is a relaxation that they have to be the same. This is a relaxation that basically say, oh, by the way, the line or the curve can continue to fluctuate, can continue to oscillate, but eventually we will settle on a particular upper bound of the upper part of the curve or the oscillation, and we can form a lower bound of the oscillation as well. Is that doing okay with your, are we relating this concept to both the textual description and also what we discussed on last Wednesday regarding just a simple limit? This is how we can solve the problem with that -1 to the power of I, because now I can just say 1 is the limit superior, -1 is our limit inferior, because it oscillates always between these two values. It would not exceed these two values as the sequence continues to go to infinity. Are we doing okay so far? So in the end, all of these fancy terms and the fancy descriptions here, they are really just helping us to understand the behavior of a sequence as it goes to infinity, and all we really care is what is the upper bound and what is the lower bound. All right? Yes, go ahead.
If you go back to that graph,
Yep.
so that graph is, that equation before is only graphing the green and the orange lines. It's not graphing the blue lines.
Okay, so the orange and the green line correspond to limit superior and limit inferior. So this is the green line. This defines the green line. The blue line is plotting out each one of these things as we go. The orange line is defining a limit inferior. So this is our orange line. I did not draw a corresponding line corresponding to the individual items that we are finding a maximum of. So each one of these is not individually plotted. So there's no equivalence to the blue line here on the flip side. I did not draw that. Are we still doing okay so far? Okay, all right. So with all of these terminology, fancy terminology, now we can start to define what is considered to be an upper bound. Now we have to understand these two functions. We have f of n is the size of a problem, which typically, is like the size of an array, number of items you want to sort, that sort of stuff. So f of n is representing the actual amount of time. So you take into consideration what kind of processor, what kind of architecture, what kind of clock speed, how much RAM, okay, and all of the other things. So f of n is an exact amount of time that it takes to solve a problem, given the size of the problem is n. G of n, on the other hand, is something that is simple, like 1 for constant time, n for linear time, n squared, n cubed, log of n log of n, and so on. In other words, G of n is just trying to get the shape of the curve right. Okay, f of n is the exact. Okay, most of the time, we don't really care about f of n. We just want to know what kind of G of n we are looking at. So the upper bound is, this is the big O notation. So when people use the big O notation, they say, oh, this algorithm has a time complexity of n squared. So it's big O of n squared. Big O is actually generating a set, okay? And in this case, we say the actual time complexity function f of n is considered an element of big O of G of n. And remember, G of n is a very simple function based on n as an estimate of what the curve looks like. That is an element. This is true if and only if the limit superior of f of n divided by G of n is less than infinity. That's the definition. It is, the way we say this is G of n is an upper bound of f of n. Okay, let me just pause here for a moment and see if you guys have any questions, just based on what I said. If you don't want to deal with the limit superior thing, just think of it as limit, because most functions that we deal with do not have oscillation. But are we understanding what that means? Okay, someone may point out right away, it's like, so if I just plug in, like a bubble sort, okay? So think about bubble sort, which has a time complexity of n squared, right? So f of n is going to be something resembling an n squared curve that grows like this. I'm going to make G of n cubed, okay? So that's going to make this term, as n approaches infinity, this is going to be 0, right? So now the question is 0 less than infinity? What do you think? Yes, it is. So that means, so are we saying that, the big O notation of bubble sort can also be n cubed in addition to n squared? It can also be n to the power 4th, n to the power 5th, and so on. The answer is yes, 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 and yes. Because all of those are upper bounds. Big O is defining the upper bound of something. It doesn't say anything about how close that upper bound has to be to the whatever we are estimating. It can be grossly overestimating. It still counts as an upper bound. Yes.
So basically, we're just testing if G of N, like we're given a G of N, we give it a G of N, testing if it's an upper bound.
Yes. But it can be grossly overestimating. So the upper bound doesn't have to be tight. It can be like way over. Yep.
If you have n log n complexity.
So if f of n itself is kind of n log n, right?
Yeah.
If the algorithm has an n log n complexity, yes, go ahead, continue.
G of n is x. Would that be?
Yeah, it will still be a valid upper bound because your g of n is still growing faster than f of n. That's all we want. It's just it's growing faster or at least at the same pace as f of n.
So, like, O notation, big O notation, basically describing the best case.
It's an upper bound, which means the actual amount of time cannot exceed g of n as n approaches infinity. But that's also the thing, is as n approaches infinity. So we okay with this concept? The big O is just an overestimate. It can be tight, can be exactly what it is, but it can be over. It's an estimate of the upper bound of how much time it takes to complete, to use an algorithm. Are we doing okay with that concept? Questions? Okay. I'm not seeing any questions. So we are going to ignore negligible for now because it's a special case of upper bound, except in this case, we have a gross over estimate or gross upper bound. So we'll focus on instead lower bound. Does this symbol or definition resemble anything that we saw earlier? Let's try to figure out, okay? I think there are some similarities. There's the element of, right? We are looking at big omega to be returning a set in this case. We have f of n here, g of n here. So from the left-hand side perspective, the only replacement is uppercase O, which is actually uppercase Omicron. It's not English O, but it's Omicron, is replaced by omega. Okay, look at the right-hand side, okay? What is changed on the right-hand side? Instead of limit superior, we have limit inferior. Okay, so, okay, let me scroll up a little bit here. Oh, too much. So instead of limit superior, this is limit superior?
No.
Oh, this is, oh, that's, there we go, perfect. No, not exactly, because this is limit superior, this is negligible, which we are ignoring for the time being. And this is limit superior. The limit inferior, right? This is limit inferior. And we are still looking at the same ratio. And in this case, we just want it to be greater than 0. Okay, so what is greater than 0? If f of n is, okay, this is basically establishing the lower bound of something. So let me think of this. Oh, I know. Let's say we are talking about bubble sort again. So bubble sort itself has a real complexity that is about n squared. So f of n is about n squared. And I'm going to use g of n, which is supposed to be a lower bound. I'm just going to say constant time, 1. We doing okay so far? So now we are looking at this limit here, but in this case, since it doesn't oscillate, we can ignore the limit inferior, which is, we can just say it's a limit. So we are now looking at something that has n squared in it, divided by 1, which is just n squared, right? And the n approaches infinity, which means what value is going to be returned by the limit? It's an infinity. Okay, and is infinity greater than 0?
Yes.
Yep. Okay, so that makes it a lower bound. Does it make it a very good lower bound? No, but it is a lower bound. Is that okay? So big omega is really just is this a lower bound of that? Is G of n a lower bound of f of n? That's all it is asking. It doesn't say that it has to be close. It doesn't say that it has to be even sensible. It's just asking, is it a lower bound? Are we doing okay so far? So now we have the upper bound, and then we have the lower bound. What do you think would be a sensible thing to do, to ask at least? Are they the same? Is the upper bound the same as the lower bound? So we're going to ignore dominant because it just talks about a Rho's underestimate in this case. So the tight bound is this, okay? And forgetting about the right-hand side of the if and only if, let's just focus on the left-hand side. Does that resemble something that we have seen already twice? The only change in this case is instead of big Omicron, big omega, now we have big theta. That's it, right? So, but what about the right-hand side? The right-hand side does not even bother to mention anything about limit anymore. There's no limit inferior, no limit superior. Why? Because I'm referring to big Omicron and big omega. So can someone kind of briefly describe what is a tight bound?
It's in both sets. It's in both Omicron and
G of n is a tight bound of f of n if and only if it is both the upper bound and the lower bound. Is that okay? Are there any questions? Is anyone thinking about how can it be both? Isn't it only possible to be either the upper bound or the lower bound, right? I mean, it doesn't make sense for the same function to be the upper bound and lower bound. So let's take a look at what qualifies as an upper bound and what qualifies as a lower bound, and then we can then answer the question of how can it be both, okay? Okay, so we go back to upper bound first, okay? This is the actual definition of upper bound. So what if I were to say this whole thing here, limit superior n approaches infinity, f of n divided by g of n, and then the absolute value of that. What if I just to say that is exactly 4? That's fine, right? 4 is less than infinity, and so g of n is an overestimate, or it's an upper bound of f of n. Are we good so far? Okay. So now we move to lower bound, and it's the same equation, except in this case, I say f of n divided by g of n is 0.5. Is 0.5 a number that is greater than 0? Okay, that's how we can have g of n being both the upper bound and the lower bound of f of n, because the constant that you need in order for that limit to work can be different. Is that okay? All right. So the next time you hear people, especially from, I guess, CISP440 from Iraj saying, the big O of something, you have to remember what big O is really representing. Big O is not what you really want. What you really want is big theta. You want to know the tight bound of an algorithm, the time complexity of an algorithm. You don't want to know just a upper bound, because that one upper bound may not make sense. Okay, yes, it is an upper bound. I know it's not going to take any more than this amount of time to get it done, but it may not even be close to how much time it will take. So what you want is a tight bound, which is known as big theta. Are we doing okay so far with these concepts? It's more of the main concept that is important. I mean, the definitions are important, okay? Because part of the objective of this class is to get all of you to kind of get used to these notations. Why do you think that is the case? Why do you think we have to get used to the mathematical definition of stuff that you may or may not see again? But in this case, I'm going to say, yeah, you're going to see this again. So there are two aspects, right? So first of all, why do we care about the mathematical definition? Yep.
Because it's precise.
It's a precise thing. And how is that going to help you with programming? I mean, all I want to do is to write some games and make a lot of big bucks and then retire. Why do I care about math, definitions? Yes.
Because we're trying to avoid making errors through being unspecific in what we want. So we have to know exactly what we're going for and do something that only does that and doesn't give us erroneous effects.
And we want to be able to describe things in a very precise, but accurate way, concise and precise at the same time. And mathematics as a language does that. And you have been doing this for 2 years already. Because guess what programming is about? Programming languages are not forgiving. You miss a close parenthesis, or you have an extra open parenthesis somewhere in your program. Do you think it's going to work? Nope. So you are used to this already. Then the next question is, in the shorter run, okay, is this going to be useful? And am I going to see this again? Is this something that I will only see once in tax class and I'll be done with it?
It's possible.
Well, it will be the case if you change your major. I'm hoping none of you will change your major because you're here, because you're already committed. So you will see this again in the upper division version of this class. That's guaranteed, okay? Unless your major is not computer science, because there you can transition to something that is not computer science, like you can transition to data science or game programming. There are a few other related majors that would take CS transfer degree here, but you'll be transitioning to something that is not computer science. But for the most part, you will see all of this stuff again.
Not only that, but it helps shape our brain in a way that prepares us to solve problems in a very concise and precise manner.
Which is basically what math is about.
Yeah.
Yep. You're correct. Because you want to write your program in an elegant way without a lot of extra code or without a lot of copy and pasting. All right, and you can see that this is pretty much the end of the entire thing. So the conclusion is big theta really is the most important notation. Got it wrong, okay? Wikipedia just say, okay, the big O is blah, blah, okay? They're not wrong, okay? The big O is that, but they want to actually say it is the big theta instead of the big O, because just knowing it's the big O is not really that helpful. Knowing it's the big theta is much more helpful. And the point is we want to find the G of n so that f of n, which is the actual amount of time that it takes to solve a problem of size n, is belonging to the G of n is the upper bound, and then it's also the lower bound of f of n. So we also, I kind of skipped over, Omicron, lowercase upper Omicron and lowercase omega, because those two are really just saying, do we have a gross overestimate of the time, or do we have a gross underestimate of the time? Because if they're gross, they're not going to be very helpful. And so even though they do have their notation, they're typically not referred to in any type of publication. So I do have to mention those because they do exist, but at the same time, they're not really that helpful. So are we good with all of this stuff here? All right, I'm hoping you guys are feeling a little bit more comfortable reading the notations, especially something like this. It's basically finding the maximum of the minimum. The question is the minimum of what? It's the minimum of the sequence with a different starting point, okay? All right, so if this is all good, we still have like 9 minutes. That's plenty of time. We'll move on to the next topic.
So, Professor,
Yes.
what is the big theta of bubble sort, for example?
What is the big theta of
bubble sort?
bubble sort? That would be n squared.
Isn't that the big O?
Hmm?
Isn't that the big O?
Well, in order to be the big theta, it has to be the big O, big Omicron, and the big
Right.
omega. So n squared is going to be both it's a type bound. So it is both the upper bound and the lower bound of the actual amount of time. Because bubble sort guarantees that it's going to be n squared. I mean, you probably want to make the assumption that the array was not sorted to begin with, right? So you want to start with an array that is guaranteed to be not sorted. So that way you cannot compare the time it takes to sort an array when it's already sorted with one algorithm, and then compare the time of that against a different algorithm and using an array that is not sorted. So that would not be a fair comparison. So we are moving on to the next slide, which has to do with recursive definition and algorithms. And because CISP440 is a co-requisite of this class, I'm hoping that you guys are now feeling a little bit more comfortable with recursion. Is that the case? Okay, very good. So we are going to start with a few recursive algorithms. The first one is totally overused. It is using a recursive version of factorial. Okay, and you guys have seen this a lot. And this is the really, really long, unnecessarily long version of f factorial, even when you want to consider to use recursion. So what I want to do is to show you the more concise way to write the recursive version of factorial. Okay. So this is Joplin. I really like Joplin because it has syntax highlighting. You guys can focus on the right-hand side when I write it on the left-hand side. So unsigned f, unsigned n. I can do it in one line. Okay, so, all right, so this is my challenge to you. I'm going to write the factorial function on one single line. So the first thing you probably want to know is, so are you combining the conditional statement into one single expression?
Yeah.
Okay, so what kind of expression is that?
Ternary.
Ternary, very good. Okay, so it has a colon and a question mark. What goes before on the left-hand side of the question mark is the condition. So in this case, what condition determines whether I have reached the end of the recursion? That I know the answer without having to call f again. I would consider 0, and I mean 1 is right too, but 0 factorial is by definition 1, so we cannot miss that one. So we might as well just use that. So we say when n equals to 0, then we know the answer is what? 1, okay. If not, okay, so now the question is, do we have to account for the fact that n is negative over here? We don't, why not? No, there's another reason why I don't have to worry about n being less than 0.
And
Yes, unsigned, right? The type of n means it cannot be negative. So that means I don't have to worry about negative n's. So what do I put here? This would be the recursive version, which is n times f of n minus 1. So that's how you can write here n factorial using a single expression. Is that okay so far? All right. So, but what have you learned here? What is the pattern that we are seeing in terms of recursion? Well, the function calls itself, right? But that itself tells you that the original problem of finding out what is n factorial can be broken up into a smaller problem by this multiplication. So the n times f of n minus 1 is the smaller operation. And then the other side of the smaller operation is to say, okay, now I need to find the factorial of n minus 1. So the nature of the smaller problem is exactly the same as my original problem. And that's why I can call the same function to do it, to solve that problem. So this is a very powerful way of looking at a problem and also looking at potential solutions. If you can break down the solution to a problem of, okay, if I break this one piece off, okay, and do something with this smaller piece, and the remaining of the problem has the same nature as my original problem, then you can use recursion. Is that okay? All right, so let's look at the next example. So the next example is Pascal's triangle. which we have already dealt with, except we did not code it. We call that what? Pascal's, instead of Pascal's triangle, is identity, exactly. So Pascal's identity explains why Pascal's triangle works. So in this case, it's kind of the same deal, except it is a double recursion thing because we have to figure out the two values on top of the one that we need to figure out. Okay, so in this way, it is a little bit like Fibonacci sequence, where one single number requires two, it breaks into two subproblems. But now would I do it this way? The answer is no. This is an awfully slow algorithm because the same value gets computed over and over and over again. But from a mathematical perspective, it is a very neat idea. Because if you ask a mathematician to prove the correctness of an algorithm like this, the mathematician is not concerned about how much stack space it's going to use, how much time it's going to use. The mathematician is only concerned about, does it give you the right answer? Okay, and every algorithm that can be expressed recursively can also be expressed without recursion using just plain loops. So that means, if I just take something like this, the mathematician says, yes, I can prove it is correct. Then you have a mechanical process that can convert it into something that is not recursive. That makes it more efficient. All right, this is my favorite, the Tower of Hanoi. And question? Okay, so it's my favorite because it is complex, okay? I don't have enough time to go through the algorithm, but I think I do have enough time to go through some demonstration of Hanoi's tower. This might be a good one. I'm not sure whether I get into trouble. Yeah, I can skip down. I would think about it. All right, so the key is once again breaking the bigger problem into smaller problems that involves some smaller steps that you have to do, but then recasting the subproblem to something similar to the problem that you were given with to begin with. So in this case, the key is to recursively say, I want to move everything except for the bottom disk to here using this pole. Once that's done, you move the only disk, which is the bottom one, the largest one, from here to here, which is single operation. And then your remaining task is to move the entire stack from here using this to over here. So that's the general strategy. So the algorithm to solve this problem is actually surprisingly simple. 3 lines of code would solve it. Now, the time complexity is horrendous because it's 2 to the power of the number of disks. So it is horrendous, but the solution, because of the power of recursion, it makes it very simple. And the way, the most important point is how you look at a problem, how you look at a bigger problem and try to break it down to something that resembles the original problem, but a smaller piece. All right, I'll see you guys on Wednesday. Yep.
I have a probability question. Probability question, right?